Alright, so for this video lesson, we're going to take a look at electric circuits, specifically looking at the components that we're going to put in them and how we're going to draw circuit diagrams, as well as taking a brief introduction into series circuits. So first thing that we have to quick cover here are the three different types of circuits that we're going to study, but they're also the three most predominant ways in which you can wire anything that has any sort of an electric grid to it. So the first type that we're going to look at is the series circuit, and that's what this video is going to spend the rest of its time with. For a series circuit, that means that we're looking at a singular path with which current is going to be able to move through. And that's the way that we're going to reference how our current is going to be able to move, is how many paths does it have. So series is a single path, which means that current can only flow from a battery back to the battery. There's no branches, there's no other ways for that charge to go. It has one way in which it can move. A parallel circuit, on the other hand, is going to be a little bit different setup, and that setup allows for that path to choose which way it wants to go once it hits these junctions within the actual circuit itself. What this does is it forces there to be more or less current at different parts throughout the circuit. And then the network circuit is the last one here. This is simply a combination between the two, which means that you can have resistors that are in series, and then later on in the circuit you have a parallel component, or right away you have a parallel component, and then within that parallel aspect you have some capabilities and the appearance and the actuality of a series circuit within there as well. So today is all about series. We'll get into parallel and network circuits later. The way that we diagram these, and this is going to be the same for all of them, right? We've got our four main components that we're going to draw here, right? We've got conductors, which is going to be the wire, right? Because if you're going to set up some sort of a circuit, you have to have wires. You have to have a conductive ability for something to allow this current to flow. You got to have some voltage source, right? So some source of charges, and that in this case is going to be the battery. Note on that battery diagram that there's a short end and a long end, right? That short end is always the negative terminal of the battery, and the long end is always the positive. How it's drawn here, the negative terminal is on the left and the positive is on the right, doesn't have to be that way all the time, right? I mean, you can put the positive on the left and the negative on the right. It's not a big deal, right? It's as long as you have the short side is negative, the long side is positive, you're good. The next one down there, the resistor, just kind of that jagged sawtooth pattern within the diagram there. Now, resistors, these can be the circuit resistors that we looked at in our Ohm's Law lab, but they can be any load that we put into our circuit. So like it says in there, right, it could be a light bulb, a heater, a motor, a speaker, an LED, a circuit resistor, right? Anything that is going to use that current and is going to use that electrical energy is deemed as a resistor. Now, each one of those, a light bulb, a heater, a motor, speaker, they all technically have their own individual diagram that we can draw, right? They all have their own symbol with which we can draw. But if we start tossing symbols at you, there's a lot of symbols. Let's just go ahead and put it that way. And we don't need you guys to memorize all of them to get the idea of what is happening in these circuits. So we've decided to consolidate this down. We're just going to consider everything to be a resistor, no matter what that device may be. And then this last one down here, right, there's a switch. So think a light switch. So you go to the wall and you flip a light switch on, you flip the light switch off. Well, when that light switch is open, that's going to be the off position, right? So think open is off. And if you look on that diagram of an open switch, the circuit's not connected. And if the circuit's not connected, that means there's no path for the charges to take at all. So if those charges don't have a path, those charges can't flow anywhere, right? Which means you're not going to get anything to happen which means the circuit is turned off. So an open circuit is an off circuit. And then right next to that, there's the closed switch, right? So you're going to have a circuit that is now fully contained. The circuit has been complete. There's no break in that circuit, which means now those charges are able to flow very, very, very freely, which means that however that circuit is designed to run, right, whether it's got light bulbs that it wants to turn on, you've got a little buzzer, you've got a motor, right, whatever it may be, can now function properly because they're going to get the electric charges that they need. So for a series circuit, if you look at the diagram to the right, that is what is called a circuit diagram. And that circuit diagram, the way that that is depicted, the negative terminal on the bottom of the battery, the positive terminal at the top of the battery, and the arrows are indicating the direction of electron flow. Remember, those electrons are always going to flow from the negative to the positive terminal. And if you look how it's set up and how it's aligned, those charges only have one path that they can take. They have to go through all three of those resistors. They have to. They don't have a choice. They have one loop that they can go through. And what makes this important and what separates a series circuit in terms of its functionality is no matter where you're at within that circuit, you're going to have the same current. And the reason behind that, again, comes from it is the only path that it can take. So if you only have one path, all of the current has to flow there. And if all of the current has to flow there, that means it's going to be the same in every single location. Now that being said, based on the strength of each resistor will draw a different amount of voltage. So if you have a higher resistor, that's going to draw more voltage. If you have something that has a very low resistance, that's going to draw lower voltage. Because that high resistance is going to mean that it's going to take a lot more electrical energy to push that same amount of current through, right? So you have to have a stronger push to get the current to move through a stronger resistor. And the order of these resistors doesn't matter. As long as they're in series, it doesn't matter which one goes first and second and third. So again, if you look at that diagram on the right, R1 does not have to be greater than R2, and R2 does not have to be greater than R3. The order of them is independent because these charges have to flow through each one of them anyways. Again, the charges do not have a choice in a series circuit. They have to flow through everything. And because they have to flow through everything, it makes this last bullet point pretty important here. If one thing fails, the whole thing shuts off. So for example, if R1 were to spontaneously melt, right? Let's say it got hot and it just melted. Well, that would mean that there would be a break in the circuit. And if the circuit breaks, there's nowhere for that current to flow. There's no connection back to the positive terminal of the battery, which means the entire circuit shuts down. And that could be true with any of the three resistors in that series circuit in the diagram on the slide here, right? If it malfunctions, there's nothing left. And again, going back to that voltage drop thing, think about Ohm's law here. If you know what the resistance is and you know what the current is, you can use Ohm's law to go and find that voltage. Right? Remember, V equals I times R. And the voltages on all three of those resistors, in this case, have to equal the total voltage of the battery. Now, if there's 5 resistors in series, the total voltage across all 5 will add up to match the overall voltage of the battery. And that kind of leads into some of the math here, right? So as we look at some of the math, if we want to know what that total resistance is, right? So let's say we want to sum everything up to get a total or an equivalent resistance. If we want to find that total resistance when things are in series, it's slick, right? We just go and we add up the 3 resistor values. So if it's, let's say the 3 resistors were each 10 ohms apiece, the total resistance would be 30 ohms. So what that total resistance means is if you were to condense everything down into a single resistor, that's what that value would be. So it's taking, a multiple, a variety of resistors that are out there and if they're in series, add them up, and it would be the same thing as putting that one equivalent resistor in that circuit. So again, to find that total resistance when in series, we just add up those resistors. Now for current, what makes current good through a series circuit is, again, it comes down to that single path that it has to travel. And because it's all moving in one path, one flow, that means we're going to have one value of current. So everything, the current through each resistor, has to remain constant. So because we have a different amount of resistance at each location with the same current, that means we're going to have a different voltage at each location. And having that different voltage is important because, again, like I had previously stated, each location, each resistor is going to draw a different amount of voltage. Now, one thing I want to point out here is the formula is written as delta V, right? So a change in voltage. Change in voltage is just another way of saying a voltage drop. And a voltage drop is how much voltage is used by that device. So our voltage drops, we're not going to see them as negative values. We're not. Even though technically you're using that voltage, so your final is less than your initial, we just take the absolute value here because you're going to take the absolute value of a battery. If you're going to say, hey, there's a 9-volt battery, it's not a negative 9 volt, it's a 9-volt battery. So same idea here, right? That voltage drop or that change in voltage, always going to be a positive number, right? And we're going to look at that and go, okay, how much voltage did this resistor use based on the total current? How much voltage did this resistor use based on the total current? And that's going to allow us to find that overall voltage of the entire circuit. All right, and so with this slide right here, we've got a little bit of practice, right, a little bit of practice here on the final slide. This will be involved in the questions that are going to be asked in the Schoology quick quiz that's going to come along with the video here. But think real quick how you're going to find the total resistance of the circuit. Again, noting that we are in kiloohms rather than regular ohms. Remember what that prefix kilo is going to do for you, right? And then finding the current through each resistor, and then finding the total voltage across each resistor as well. So a few hints, right? A few things to remember, right? For that total resistance, just want to add those up. Your current through each resistor has to be the same, and the voltage across each resistor has to add up to the total voltage of the battery. So there's your introduction into circuit diagrams, which again we see here in this diagram to the right. That's how we draw our circuits. So little intro to terminology, little intro to how we draw them, and then a little discussion on series circuits. So go ahead, take the assessment. I hope it goes well. And remember, if you have questions, you've got 3 physics teachers that you can come talk to.